Have you ever stopped to think about how much energy we just waste? I mean, the heat pouring out of your car's exhaust pipe or billowing from a factory smokestack. It's a massive amount. But what if we could actually grab that lost heat and spin it directly into electricity? Well, a team of scientists has figured out a way to do exactly that. And it all comes down to an incredible material that's only 1 atom thick.
Okay, so before we dive into the really cool science, we've got to wrap our heads around the sheer scale of the problem we're up against. It's an issue that's happening all around us all the time, but for the most part, it's completely invisible.
So let me ask you this. When we burn fuel, to power our cars or light up our homes, where does the majority of that energy really go? The answer is, well, it's not what you'd think. The hard truth is, a staggering amount of it is simply lost. It just becomes waste heat. It pours out of our tailpipes, it radiates from giant industrial machines, it floats away from power plants. This is energy we've already created, but we can't use it. And figuring out how to recycle it is one of the biggest challenges in the world of clean energy. So how in the world do you capture something as slippery as heat and turn it into useful power? Well, the solution lies in a very special group of materials that can basically perform a type of modern-day alchemy. They're called thermoelectric, and the principle behind them is actually beautifully simple. If you heat up one side of the material while keeping the other side cool, it just generates electricity. That's it. No moving parts, no emissions, just a straight-up conversion of heat into power.
But, of course, it's never that simple, right? The real challenge, as this quote from the research paper hints at, is making a material that is amazing at two things that are usually polar opposites.
So here's the fundamental puzzle. You need your material to be a fantastic conductor of electricity, so electrons can just flow right through. But at the same exact time, you need it to be a fantastic insulator of heat, so it blocks the tiny vibrations called phonons that carry heat. And the problem is, materials that are good at one of those things are almost always terrible at the other. It's like trying to build a pipe that lets a fire hose of water through but stops every bit of warmth. That's the thermoelectric dilemma.
So to solve this impossible problem, scientists had to stop thinking big and start engineering on an incredibly tiny scale. I mean, we are talking about manipulating the literal building blocks of the material itself. So what you're seeing here is a peek into the secret structure of a material. It's not just one solid piece. It's actually made up of tons of microscopic crystals or grains. And the really important part for our story is that little border where two of these grains touch. That's called the grain boundary. And this is where the genius idea comes in. The scientists wondered if they could engineer those boundaries. Could they turn these little interfaces into a kind of smart barrier? One that would slam the door on those heat-carrying phonons, but give the electricity-carrying electrons a VIP pass to go right on through.
And to build this incredible super barrier, they turned to one of the most famous, most fascinating materials discovered in the last few decades.
Graphene. Yep, that stuff. The sheet of carbon that's only 1 atom thick, stronger than steel, and has some just unbelievable electrical properties. The researchers had a wild idea. What if they could wrap each individual grain inside their material with a perfect little jacket of graphene?
And would you look at that? They actually did it. On the left, you've got the concept, right? A single grain wrapped up in a perfect layer of graphene. But on the right, that's the real deal. That's an image from a high-resolution electron microscope, and you can actually see those layers of graphene, just 2 to 6 nanometers thick, perfectly separating the grains. I mean, that is thousands of times thinner than a single human hair. It's incredible.
So here's how this magic trick works. That ultra-thin layer of graphene acts like a super selective filter. When the heat particles, the phonons, try to cross the boundary, they get scattered and blocked. It's like waves crashing against a seawall. But the electrons carrying the electricity? They barely even notice the graphene is there. They just cruise right on through. They solve the dilemma.
Okay, so the theory is solid, the microscope pictures look absolutely stunning, but does it actually work in the real world? Let's take a look at the data, because the improvement they saw is pretty remarkable.
So check out this chart. It shows you exactly how good that graphene barrier is at stopping heat. By adding it, the researchers cranked up the thermal resistance at those boundaries by 3 to 5 times. Just think about that for a second. That's like swapping out a flimsy screen door for a thick, insulated brick wall, but just for heat. And what does all that clever engineering get you when you build an actual device? It gets you this. A 24% jump in the overall efficiency of converting heat to electricity. In this field, that is a massive leap forward. And when you look at the hard numbers from their test, the results are crystal clear. The standard version of the device had a conversion efficiency of 6.8%, but the new one, with the graphene hack, 8.4%. And just look at the power output. It jumped from 3.1 watts to 3.8 watts. This isn't just some interesting thing in a lab. It's a real, measurable upgrade. Now, this is about way more than just one new material. This whole technique of grain boundary engineering basically gives scientists a brand new toolbox for building materials from the atom up. So what does this all mean for us?
Well, the potential here is enormous. I mean, imagine cars that get better gas mileage because they're recapturing energy from their own hot exhaust. Or picture factories that help power themselves by recycling all the heat they generate. This is a huge step in that direction, and the technique itself could be used to improve all sorts of other materials for all kinds of other jobs.
And that really leaves us with a final, pretty mind-blowing thought. This research proves that we can now design and build materials with atomic-level precision to solve various specific problems. And it really makes you wonder, if we can now engineer matter at this fundamental level, what other huge global challenges, from clean water to better medicine, are finally within our reach?